Cool. Hello, everyone. Welcome to the first MLOps for the semester. Today we have Zheyang with us, and he's a PhD student here at UW, advised by Professor Dimitris Papiliopoulos. And he will talk today about his work, Everything Everywhere All at Once. LLMs can in-context learn multiple tasks in superposition. Zheyang.
Okay. Hi, everyone. I'm Zheyang, and so this talk, I'm going to present this recent paper from our group, Everything Everywhere All at Once. LLMs can in-context learn multiple tasks in superposition. Okay, so I think most of you have probably know of large language models, but I'm going to briefly introduce this. So we can think of large language models as decoder-only sequence-to-sequence models. And those models have been trained on massive task corpus. Like, for example, the screenshot on the right is the C4 data set, which is a clean version of the common crawl data set. And large language model has been trained autoregressively, meaning that it is trained to, so given a prompt or given a task, it's trained to predict the next token or the next word. And given another task, it will predict the next word and so on. So
I have a question. Sorry, double question. Sure. So there's this encoder and decoder. So when you're training, you have both, and when you're inferencing, you just have the decoder. Is that correct?
No. So for most of the modern large language models, yeah, it's like GPT. We use the.
So then, what's the encoder for? I guess no one talks about that.
So when the transformer has been invented, at first there's a encoder decoder structure, and for example, it can be used for say translation. Yeah.
So like the encoder maps you to a certain latent space,
right.
And the decoder comes back to.
That's right.
Language.
That's right.
Okay.
But yeah, as time goes on, people start to just using decoder as well. Cool. And one remarkable thing that LLMs perform is that it can perform in-context learning. So what does that mean? So here are two examples. On the left side, we consider the task of fixing the typos. So here we have four in-context demonstrations. So fixing the word goat, fixing the word snake, bird, and fish. And there is and at the end we have a query. So we would like the model to predict the next word by performing the task. And the model can correctly, so this is an example from GPT-3, and the model can correctly perform this task of fixing the typo, and the output is changed. On the right side, we consider another task of translating English to French. So similarly, we provide four in-context demonstration, and then we provide a query at the very last, and it can also correctly perform the task with this latent.
Sure. I'm gonna ask a lot of questions.
Sure.
Yeah. Does the delimitator matter here? Like if I separate them by a comma or a semicolon or a space, like how does it know this is not all just one big word? Does it make a difference when you're doing complex words?
So good question. So the delimiter doesn't that much matter. So so the language model has been trained on a massive task corpus. So during its pre-training, it has learned that the use of, let's say, new line or comma or
any of those will work. But if I just pass them, so go to the next slide. If I just pass them that whole thing, no spaces, no commas, nothing to separate them, would it still be like what we expect, or would it consider some of the words like go and
yeah, I think right. I think if we do that, not sure about GPT-4, but the less performant model might mess up. Okay, so one thing about this in-context learning is that so in those two examples, in the prompt, those in-context demonstration contains task examples from only one task. So on the left side, we have the prompts where the demonstration are from the fixing the typo task. And on the right side, we have the examples where those demonstrations are from the translating English to French task. So a natural question to ask is what if we provide multiple in-context demonstration in the prompt? So meaning that what if each demonstration can come from different tasks? So we actually run this experiment. Not sure if you can see clearly here, but on the left side, we consider two-digit addition in a variety of languages. So for example, we consider 4 tasks, numerical addition and addition in English, French, and Spanish. So for each prompt, we sample, we form the prompt this way. For each task, we sample 20 task demonstration, and we randomize those orders and put it in the prompt. And after that, we form a query. So here, with, for example, this prompt, we have, for example, 11 plus 26, right arrow 37, it corresponds to the numerical addition task. And the second line corresponds to addition in French text and so on. If we put this query here, we can see the output probability being like 174, having 52%, and performing the addition in English test having about 10%, and having the addition in French text about 10%. And the last test, addition in Spanish, the probability of this correct outputs is about 20%. And they all add up to nearly 100%. And similarly, on the right-hand side, we consider 3 test scenarios. So those 3 tests are that given a country name, we name the capital name, we name the continent name, or we just capitalize the whole thing. And as we can see from the output probabilities from Llama 3 model, those correct outputs of performing each task are non-negligible, meaning that they are a portion of the whole output probabilities, and they all sum up to near like 80–90%. So this is an indication that large language models can do some those multiple in-context learning tests at the same time. And as a side note, I would like to briefly introduce how we calculate the probabilities. So say I is the input prompt, and let O be an output string that we want to consider, that we want to calculate the probability. So the probability of input, so the probability of output given input is the probability of the output sequence given the input sequence. And we calculate that using a product. So basically, given the input, what is the probability of the first output times having the first having the inputs with the first output, what is the probability of the next output, and so on. We calculate that as a product, and that's how we get these probabilities. So,
so how do you decide the capital N when you are doing each term?
So the good question. So for the so for example, for its task, we know the correct outputs, and the way we measure that is that we pass those strings into the tokenizer. So for each model, there's a fixed tokenizer during inference time, so that we can just feed in the input string to tokenizer, and it will return us a output sequence of tokens. Okay. And we want to see if this phenomenon is universal. So we test. So what we had before is only one prompt, right? And sure.
Go to the last slide. The last one before that. Yeah. So I thought that these probabilities were like coming from your whatever softmax
Right.
over all your possible tokens. Right.
That's right. Yes.
So what is all your possible tokens? What is the dimensionality of that softmax algorithm?
The dimensionality is the size of a vocabulary size.
How big is that?
I think it's, let me see. So for GPT-2, it was 50K, but for
So you just sort them and then take out
Yeah.
the top three of them.
but for this Llama, for example, Llama 3 model, I think it's much larger than 50K, like 500K or something. Sorry, 100K about. Yeah.
So the model, like input size is, yes, 100K and output size is 100K.
You can think of that way, but
Not really. Input, we have like
right,
token.
we have the tokenizer
I
that
guess
we.
the output is R50K dimensions, right?
I mean, if we add those input embeddings and output embeddings,
Yeah.
it is. But we usually will convert those one hot inputs, that is the size of vocabulary, to a hidden dimension, say 4096, and we feed that into the model.
Okay.
Cool. Okay, and we would like to see if this phenomenon is consistent across different scenarios. So in each two scenarios, we form 100 prompts, and we calculate the distribution of the output probabilities for each task. So and we also consider three models. So here we have GPT-3, Llama 3, 70 billion, and Q1 1.5, 72 billion. So so for the first scenario, we have 4 tasks, and the other category, it is the sum of all other probabilities of all other outputs. And as we can see here, if we only see the median points, so here we draw the box plots, meaning that we plot the 0, 25, 50, 75, and 100 percentile, with the 25 to 75 percentile being colored. If we only see the median of the probabilities, we can see that, I mean, except for the French, addition in French for Q1, 1.572 billion, and addition in Spanish for this model, or other models has the median that is non-negligible, like meaning that it is greater than or equal to 10. So it is an indication that LLMs can perform multiple tasks in context, because those median probabilities are around greater than 10%. And we can also see from the second figure here, we can see the similar observation. And here, another observation is that we can see that each model has some different preferences. So for example, say consider the second scenario here. The GPT 3.5 model kind of prefers the first tag, naming the capital test, with a median probability being like around 50%. And say Q1 1.5 is preferred to perform the naming the content task. So I mean, that's kind of interesting, but we also test the second two scenarios. So on the left-hand side, we have test copy. So given a inputs that is 2 operands. So for example, 73 and 95, the task is to either copy the first operand, copy the second operand, or add two operands. And on the right-hand side, we consider the scenario of 4 tasks. So given a string, a word, the task is to either output the first letter, the last letter in lowercase, or the first letter or last letter in uppercases. So in those prompts shown here in examples, the output probabilities of the correct outputs of each task are quite high. Like say for the first scenario is around 30%. For the second one, it has 3 of the tasks has about 10%, and one of them has 38%. And we also plot the same thing here to see if it is universal. So the first setting, I think the median probability is kind of uniform, meaning that it is all close to 33%. And for the second setting, we can see that the last letter lowercase and last letter uppercase, those tags are kind of harder for the models. But for the 2 tasks, first letter lowercase and first letter uppercase, the models can simultaneously perform these 2 tasks in most of the cases, with the other case, which we denote it as noise, being a quite high.
So the in-context learning task is indicating the last letter only, or is the normal perform? Because maybe first letter is even last letter, so that could.
Right. So we think that the model can have some primacy bias, that whatever it sees first is to retrieve that is probably easier than retrieving the last letter. Another thing can be due to tokenization. Right. So basically, when we process things, we tokenize the letters. We tokenize the words, and sometimes we merge those words. We merge 2 letters into 1 token, and so basically, in most of the cases, the last letter can be merged with some other word, can be merged with some other letters as a single token. So that can make this harder. But anyway, those are indications that a large language model can perform multiple tasks in context. So that leads to our first one, that large language models can in context learn multiple tasks in superposition when provided with prompts of mixture of text samples, like the one we have before. So we can think of this conceptual model. It is informal, but we can think of that as the probability of output given the prompt can be roughly as the summation on task, where we take a product of the probability of output given task and prompt times probability of task given prompt. So as some sort of Bayesian here. Okay, so we have seen that in pre-trained models, the model can in context learn multiple tasks in superposition. How does task superposition emerges in LLMs during training? So one thing is that most likely the models was not trained on samples where we provide multiple tasks in context. And another thing is that model is trained on cross-entropy loss on the one-hot labels, meaning that the expected output given a prompt is 1 on 1 single tokens and 0 on other tokens. And the model was not trained on, for example, on like 0.5 on 1 tokens and 0.5 on the other tokens, like what models behave previously. So we would like to know how this superposition phenomenon emerges. So we actually train a GPT-2 model on 2 scenarios. The first scenario, we consider the following 8 retrieval tasks. So we call them retrieval 1 to retrieval 8. So the input has the following form. We have 8 characters. So each characters are drawn randomly. And the output is the one of, sorry, this should be character 9. So the output is one of character 1 to character 8. So for example, for the retrieval task, read 5, the output of this given inputs is to output K. And then we train the model using ICL training. So what does that mean? So to form a training sample, we first randomly sample a task T from retrieval 1 to retrieval 8, and inputs for each demonstration x1 to xm. So for each sample we have m in context demonstrations, where xj is an 8-character long string. We then form a sequence S. So sequence S are m pairs of x and y labels, where gt of xj is the output of correctly performing test T on the inputs. After that, after we form a sample, we consider model M parameterized by theta. We minimize the following loss. So what does that mean? Recall that we have a sequence of m pairs of inputs and outputs. So we consider n minus 1 inputs, where each inputs are having the length j, where j is from 1 to n minus 1. So for example, we have x1, gt x1, x2, that is the first input, and x1, gt x1, x2, gt x2, x3, that is the second input. Then we have n minus 1 of them. So for each input, we calculate the cross entropy loss between the actual outputs of the model and the expected outputs. We take a summation and we take an average. After that, the loss is trained we take an expectation summing over all possible sequence. So basically, we randomly samples those sequences and we take the loss. So here is an example. So say m here equals 5, and we consider the same retrieval task. So basically here we have 4 losses. So the inputs are the first line and second line up to the right arrow sign, and we calculate the loss at 6 is position. And similarly, we calculate the loss at L, 1, and X. We calculate the loss between the actual outputs of the model and the expected output here labeled, highlighted. And this is how we train the model. And after we train the model, so during training, as we can see, each training samples only contains examples from one task. But during test time, we do something differently. So during test time, we form the prompts where this demonstration comes from 2 tasks. So for example, here we have, so here, say the prompts has 20 in context demonstrations. And we vary the ratio of in-context example distribution, meaning that, so for example, if lambda equals 0.5, we have 10 examples of retrieval 2 and 10 examples of retrieval 6. And if it is 0.1, we have 2 examples from retrieval 2, and the remaining examples are from retrieval 6. So we vary those ratio, the in-context text example ratio from 0 to 1. And we can see that even though the model is trained to learn each task, one single task, even if the model is trained to learn a single task, during test time, if we provide the model with prompts of two text mixture, it can still interpolate the output probabilities, meaning that so what I mean by that is in training time, we only have examples correspond to lambda equals 0 and lambda equals 1, corresponding to task samples of one task. And during test time, if we interpolate this ratio like we did on the pre-trained model, it is able to still calibrate its output probabilities along with the task example distribution. And similarly, we consider the second scenario. So the input is a number, it's a 2-digit number, and the output is to add from 0 to 9. So basically, itself plus 1 to plus 9. For example, plus 3 corresponds to 12, right arrow 15. We observe the similar things. So the model can also, even if it is in context learning one task during the training time, during test time, if we provide a text mixture of 2 tasks, the output probabilities can still align with the in context task sample distribution. So this leads us to our second finding, meaning that even if the transformer is trained to learn one task at a time, it can still learn multiple tasks in superposition during the test time. Cool. So in the previous part, we've seen that it can perform task superposition from a model that we trained from scratch. And now we switch back to the pre-trained models. And we would like to see how mechanistically how task superposition manifests in the pre-trained LLMs internally. So what mechanism cause the LLMs to perform this task superposition? We would like to introduce a idea called task vectors, it is introduced by Handel. And so they are vectors in the embedding space, so that are found to encode the algorithm that a model internally implements to solve a task given in context demonstration. And what does that mean? So here are some details. Don't worry if you get lost. I'll provide you example afterwards. But so for example, we consider the task copy operation 1. So for example, for 12 add 72, the output is 12. So basically, the task of copying the first operation. So the first step is to collect a data set of, say, 100 ICL sample prompts, where each prompt consists of 60 in context demonstration, and plus a query. So for each pair of inputs and outputs in the demonstration, xj, yj follows the form operand 1 at operand 2 equals, sorry, this should be operand 1. So the copy operand. And for each prompt p, we form the prompt the following way, like we did before. we concatenate those in context. We concatenate those in context demonstrations together, and there are m of them, and we concatenate the query at the very last. We feed the prompt into the transformer model M and extract the feature at the last equals to at layer L, denoted as MPL. Then we average this vector, which is the feature at layer L across all prompts to get a vector VL. This is the vector we get at the layer L. Afterwards, for each layer we have a vector, and then we run a forward pass with one query X, and patch the vector VL at layer L. This simulates a complete context, and repeat this process 100 times for different query X and get an accuracy of accuracy L for layer L. Then we define the test vector layer L star by maximizing the accuracy. So now we have the test vector layer. Then finally we define the test vector, the copy operation 1, to be the test vector at the test vector layer. And here is a demonstration from the original paper. Basically, so there are two steps. The first step is to get the vector here at layer L. So we have a demonstration and a query X, and we extract the vector at the, here is the right arrow sign at layer L. And then after we extract this, for a new query, say here is a corn, we patch in the test vector here at layer L, and it gives us a simulation of the complete context, and we have the output. We calculate the accuracy for it. So if you are still confused, you can just think of that as a vector that represents the task. Okay, so how does that connect to our story? So what we did is that we plot the test vectors.
So go back to the so what you're doing is task vectors. My understanding is there's this idea that maybe task vectors are in large language models. You guys are training large language models that they have a task vector, or
okay, so no, we are not training. So here we are not training the.
So this is like a conceptual model. Like what could be going.
No, this is how we extract the test vector given a large language. Okay, sure. So yeah, so for example, for the copy task, we can have 100 prompts, and we use 100 prompts to extract the test vector of copy task. And we have another task, we use 100 prompts to extract the test vector of that task.
Yeah, I like that.
Okay, so we consider two scenarios. Where the first scenario has 3 tasks: copy operation 1, copy operand 1, copy operand 2, and operand 1 plus operand 2. We plot the task vector of these individual tasks. So at the very and so here the pink one and the yellow one and the green one here. And we also extract the task vector of using the text mixture prompts. So for example, here at 100 correspond to all prompts being where all the task demonstration are from copy operation 1, copy operand 1, and 010 meaning that all demonstration comes from the task of the second task. and the 001 correspond to the prompts where all demonstration come from the third test. And we also consider mixture. So for example, 0.5, 0.50, meaning that 50% are from the first test, 50% are from the second test, and none from the third test. We also have 0.5, 0.5, 0.5, 0.5, and uniform mixture, which is 0.33, 0.33, and 0.33.
So you take the test vectors in PCA basically.
Well, we here use LDA, but yes, we plot those test vectors extracted from the different text mixture prompts, and we plot those test vectors here. So as we can see, the test vector of individual tests are scattered around the corners, and the uniform text and test vector of the uniform text mixture are roughly centered at the middle. And for example, here this green dots correspond to test vectors of prompts with only the first and second test. So the test vector lies roughly in the connecting line between those test vectors. So we see this as an indication that probably LLMs internally combine those test vectors during test superposition. And the second, so given this, we know that LLMs internally combine those test vectors. We wonder whether we can reproduce this test superposition by just convex combining those test vectors manually. So we did that. We just so for say we have test copy operand 1 and copy operand 2. We make a convex combination of test vector. We interpolate lambda, where lambda is the mixture ratio, and we mix it by a ratio of lambda of the first test vector and 1 minus lambda times the second vector. We patch the interpolation of the test vector into the model, and we plot this. We make this plot. So the upper rows. So the upper row is the correspond to how for those output probabilities if we patch in the test vectors of the convex combination, and with x-axis being the lambda, the mixture ratio, and the bottom row correspond to the how we correspond to the in context examples. So this is kind of like a baseline we have before. So again, the top rows are the convex combination of test vector that we manually set, and the bottom rows are our probabilities if we provide the text mixtures. So as you can see here, so for example, for the first scenario, we consider copy operand 1 and copy operand 2. We can see some kind of interpolation between probability 1 and 0, and we can see the test superposition at, for example, 0.5. There is the probabilities are roughly 50-50 split. But another thing we can see that compared to the ground truths, the baseline, if we only convex combining those test vector, we can see a larger noise here, labeled by the other category. So meaning that even though LLMs internally combine those test vector, it is beyond just convex combination, and that makes sense because neural networks not just linearly transform those factors. There's some nonlinear transformation there. But still, we can see that the convex combination is sufficient to reproduce some kind of test superposition.
So I have a question on the right hand side, where y for the interpolation in context is too bigger, the endpoints on the x-axis, so lambda being 0 and 1, they are different. I thought for these, the test vector should not be either interpolated for in context there's no mixture of tests, but y, like for example, when lambda is 0, it seems like there are more other.
That's a good question. I think it's because the way we calculate test vectors. So here those probabilities are. So here we calculate the probabilities by inputting a single prompt, the mixture of prompts. But here using the task vector, I mean, but here the task vector are calculated by averaging the task vector. So so the first reason is that probably averaging those task vector cause some noise. And the second thing is that we only use task vector to simulate the context. Right, I think that's still a little bit different from having a complete context.
So you mean on the top, it is injecting the test vector to a zero-shot prompt,
right?
The performance of that. So there is some performance variation because of that.
Right. Cool. Okay, and that's our first one. That's our fourth finding, which convex combination produce test superposition. So as our last question, how we've seen those interesting phenomenon of test superposition. We wonder how models' test superposition ability change as the model scales. So we specifically we consider two questions: whether larger model can perform more tasks in context, and whether larger model can align their output distribution more closely with the distribution of test examples provided in prompt. So we consider the following. We consider following metric. So the first metric measures roughly measures the capabilities of how the models perform multiple tasks in context. So given the prompt that consider demonstration of say K task, we define R to be the number of the tasks whose correct answers appear among models top 10 most likely outputs. So note that here R is less than or equal to K. So that's the first metric. The second metric we use is to align how well the model aligns the output distribution with the distribution of test demonstration. We use the K-out divergence. And we consider the 6 tasks here. So the 6 tasks are just that given a 2-digit integer, we output the integer itself, the negation of the integer plus 1 minus 1 times 2 and the square. So we consider a set of 6 tasks. And we consider a Q1 model, which has a scale from 0.5 to 14 billion. We plot the R values and the K-out divergence. So on the left side, we can see that as the and we also use 3 different task examples distribution. So for D1, it is the uniform distribution. For D2, it is a spiky distribution. So there's one task having a very large probability, like say 0.5, and other task being having some equally small distribution. And D3 is the distribution of alternating large and small between test 1, test 2, test 3, test 4. So for example, we have 0.3, 0.1, 0.3, 0.1, those kind of alternating test distribution. So as you can see under those 3 in-context test distribution, on the left-hand side, as the model scales, the R values, so the number of tasks whose correct answers appear in the top table, most likely outputs increases, indicating that as we scales the model, it can perform more tasks in context. And on the right side, we can see that as the model scales, the KL divergence, the discrepancy between the in context test distribution and its actual distribution decreases. So that's the indication that LLMs for under the same LLMs family, the bigger model can solve more tasks in parallel and better calibrate their ICL distribution to their output distribution. And that's everything experiment and the finding for our paper. So so we show that LLMs are a superposition of simulators, meaning that it can execute multiple tasks simultaneously, and we show that it internally combines test vectors. However, one limitation of our paper is that we explore a weird superpower of LLMs, but currently it has limited practicality, and this means that we can probably design a better decoding algorithm because we show that LLMs is not just doing one thing when provided the problem. It can actually do multiple things. So there's a recent decoding algorithm called Superposition decoding. So basically, in their decoding algorithm, under one single pass, the model, we can use this decoding algorithm to give us multiple outputs. And so those kind of decoding algorithm can be more effectively, use the this superposition of power of LLMs. And there is also an implication for alignment. So if we think of those current, say, RLHF alignment, we train the model using RLHF reinforcement learning or the DPO by aligning the model with the desired output we want. So for example, we don't want the model to perform bad things. Essentially, we're training the model to surpass the bad behavior. But it could be the case that, however we surpass those output probabilities, those probabilities still exist there. And the LLM still has the capability of doing those tasks, even though it has a very small probability. And it could be the case that those behavior, like the jailbreaking strategy, many-shot jailbreaking works, is that by having a very long jailbreaking input, those bad behavior, those probability just increase as we provide examples of many bad behaviors. And yeah, so that's everything for this talk. Thanks. And if anyone has any questions.